All right, guys, I think we'll keep moving. So, just a few further comments to add upon what Louis already said. So, with Underworld 2, we don't actually provide much implementation at all, really. I mean, our main focus really is to provide you guys the building blocks and then let you guys go ahead and define your own physics, I think. During the Monday session, there was some discussion of Underworld, and there was another application, I can't remember which one, and they had some definition of a Rayleigh number, and the issue was in the end that their respective definitions of Rayleigh numbers were different. In Underworld, you'll never find a definition of a Rayleigh number. So we provide you the tools to go ahead and calculate your own Rayleigh number. So, I mean, the best thing in letting you guys define your Rayleigh number is that, well, you know exactly how it's defined. So really that's kind of the way we approach things in Underworld 2. So like I said, kind of a core set of functionality. We expose data where appropriate directly via NumPy arrays. Who's used NumPy here, can I ask? Right, so NumPy is it's basically the standard Python language for any numerical data. And it just gives you a nice interface to accessing arrays of data. Now, the beauty of this is that you can go ahead and you can outsource a lot of functionality to, I mean, plenty of tools that already exist. Python is just a huge world of scientific software out there that now you can leverage and integrate in your Underworld models directly because we expose the data. The other thing that we really want to be doing well now is interactive model development. So you'll see today we're going to be running all our visualization is integrated in notebooks. We want you to be using, again, like the autocomplete and trying things and modifying results and trying again. The idea is just to get your models up and running fast. So really we just want to bring that model development time down, which then lets you spend more time thinking about the actual science. I'll also point out that we're still kind of it's still a beta release. So you'll probably come across some things that are maybe a bit broken, or at times things will explode and stop working. We're pretty close to what we'll call a stable release, but yeah, not quite there yet. So, okay, I'm going to go ahead and actually just import the Underworld module itself here, right? So, typically you're just going to run something like that. So this line here, import Underworld as UW, so we were just creating a little shortcut here to our Underworld module. I mean, how many people here are not super confident in Python? Okay. Not reasonably confident in Python. All right, well, I mean, we don't... possibly. We don't use any particular hardcore Python functionality. I think it's all pretty straightforward, and usually it's pretty illiterate kind of language. I think you can usually get a fair idea of what's happening even if you aren't a Python guru. So just to confirm,
but feel free to interrupt, right? So
of course.
Oddities about Python that can be very quickly cleared up. So people who don't realise what the difference between square brackets and round brackets and stuff just yell, why did you change from that to that, here or there? No one else is going to care. You went through it.
So we can check the version. I think you should all see version 2.03 beta 2, current designation. Right, so I'm going to kind of step back now and give you guys a quick tour of our visualization engine, because like I said, it's really integrated in everything we're doing in the notebooks. So it's called GLucifer. It's been in development for a good 10 years actually, through the original Underworld and now Underworld 2. It's fully geared for running on big supercomputers. On that front, we have a tool called the Visualization Store, which allows you to save your visualization data on your big supercomputer simulations and then download it locally onto your PC and actually still interact with your visualizations, rotate, change various attributes of your visualization, etc. And really that's kind of the way you typically want to be using things. You're not going to really know exactly where you want to look at a model before you run it necessarily. There's also a standalone version which allows you to launch against a visualization store directly from the command line. We don't need to worry about that too much for now, but it does allow you, when you get to doing very large simulations with lots of particle counts, it allows you to run across some more serious visualization hardware. We have WebGL integration, which we'll have a quick play with today. Not all of the visualization tools are integrated into WebGL yet, so just keep that in mind. And finally, just for those of you who like ParaView or want to use any other tool, we can export all your data as XDMF files, which allows you to fire them in ParaView or Visit or whatever. So, we're not forcing you to use GLucifer. You can use whatever visualization tool you like. Like I say, because it is integrated in in your notebooks, I think it's well worth using Underworld. I do think it's well worth actually getting a handle on using GLucifer. But as we'll see, it's pretty straightforward, I think. So there are two main classes in GLucifer. The figure class, which is really just your basic container where you're going to take a figure, add whatever visualization data you want to it. So it's really a blank canvas for whatever visualization data you want to use. And the drawing objects are the visualization data. So the ones we're going to look at today are mesh, which renders a mesh. There's a surface object which will draw a function on any surface, so functions will come too soon. And then we have a points object as well, which you'll typically use for swarms. So likewise, to use GLucifer, we just import GLucifer. I just wanted to remind you guys that in the notebooks, if you tack a little question mark on the end of an object, try this, syntax, it doesn't want here. Why is that invalid? Let me try this. Right, it will actually break up the documentation for that object there. And it'll drop down menu. Or if I go GLucifer.figure, question mark, and likewise it gives you the documentation for that object itself. So here you can see you've got all the various parameters you can pass in when you're making your figure and a description of those parameters. Throughout the code, we've really tried to stay on top of the documentation. So most things should have a pretty good set of documentation or doc strings, as they're called in Python, alongside them. So anytime you hit that question mark, hopefully you'll get some sort of useful information about that object. And we can close that just like that. So to create a figure, let's just do that. There it is. We've just created a figure, nothing in it yet. So I'm going to quickly make a mesh now. We'll come back and have a closer look at mesh shortly, but just for the visualization's sake, let's go. Then what you do is you append. So you append objects into your figure. So now to find the objects, it's in the GLucifer objects module, and we want the mesh object. So again, right then I hit Shift Tab. And when you hit Shift Tab, you get all the options for that particular function or class constructor or method. So in this case, okay, for those again not super familiar with Python, you see this self object at the start. Ignore the self object. You never need to pass in a self object. So really, it's from the second parameter on, and it's really just asking for a mesh. And there's a few other options, but we're not concerned with them for now. And there we go. Now we can actually go ahead and draw that. It's just as simple as that. Just like to point out, all the slides for the presentations today are available via that link. I'm going to be jumping around a fair bit because there's only so much screen real estate I can work with. So it might be worthwhile grabbing those slides so you can, not be too concerned with something that's gone off screen. Right, on to mesh. So currently all the mesh that are available to you are what we call curvilinear structured mesh, right? So basically it's a mesh which, let me just forward. Typically this is going to be the first mesh you're going to generate. Anytime you generate a mesh, it's always going to come out in this regular geometric fashion. When I say it can be curvilinear, you're free to move any nodes wherever you like. Of course, you have to maintain the mesh integrity. You can't just tangle nodes up. But when we say it's structured curvilinear, we mean that you can start at one corner, and if you walk along those elements, you always end up at the opposite corner. So it's not unstructured where the connectivity of the nodes is arbitrary. Okay, it will define your finite element geometry. So your mesh boundaries are really going to define the domain over which you're actually simulating or you're doing your numerics. And likewise, it will define your resolution and the order for your finite element method. Furthermore, your parallel decomposition, when you're running in parallel, is going to be completely determined by your mesh object. And it will be static for the entire simulation. We'll see how we go for time later. I might have a quick run through of some parallel considerations. Once again, this is just a regular mesh. This is always going to be the first mesh you see when you use your mesh constructor. You can see here we've got a swarm of particles embedded in the mesh. So typically, in this kind of simulation, you can use a relatively simple mesh, and then you leverage your particle data to introduce complex geometries into your models. It's very straightforward to construct some sort of, if you want to do some sort of regional simulation, it's pretty straightforward to modify your mesh into something along these lines. And here's another mesh where, we've actually conformed the mesh to some topography of the domain here. So we did see making a mesh. Let's go ahead and make another one. So mesh Cartesian. Again, Shift Tab to get your constructor options. Let's have a look at element resolution. So typically you're going to specify your mesh in terms of tuples, IJK tuples, so one for each coordinate axis. So let's make a 2D mesh. Let's make it 16 by 16. Again, I'm hitting Tab to autocomplete. Don't forget that one. You're going to specify the lower left, say, corner of your mesh. Let's just put that at 0 and 0. And likewise, you'll specify an upper right coordinate. Now let's put that at 1 and 1.
I have one question.
Yep.
One of your examples here is the convection example. I see here element type Q1 over DQ naught.
Yep.
What is that?
So typically that's defining, whenever we're doing any kind of Stokes simulations, we typically define a pair of elements. So it's, what is it, Q1 over P naught? So it's really a Q1 primary mesh, which is Q1 is a linear quad mesh. So, and the Q1, it's DQ naught? DQ naught. So that is a constant discontinuous element type. So you've got one node at the center of each element there, right? That naming convention follows who published that, the element? Periodic table of finite elements. So, yeah. Yeah.
Comprehensive. It's not comprehensible.
Well, that's right, on account of its comprehensiveness, somewhat.
Can we go 3D here?
Yes, I'll come to that in 1 second, certainly. All right, so let's just quickly grab another figure. Well, we're going to do GLucifer objects mesh. Let's tack that inside, and let's look at that. All right. So what I'll do is pop that in here, like that, and then I can go. So if we did this, you should be able to see. It's very straightforward to modify things. So every time I'm running this command, I'm creating a new mesh object. The previous mesh objects will usually just disappear. It all just depends on Python. If something still uses that, needs that mesh, it will still be retained. That's just Python garbage collection kind of rules. But you don't need to worry about that. Right, 3D. So 3D, this time we just specify a kth dimension, let's say. Now, that will fail, right? Now, just have a look at the error messages. We try and make them useful. We don't always succeed, but read them at least, and then hopefully it'll give you some indication. So in this case, saying min coord tuple length 2 must be the same as that of the element's resolution, which is a size 3. So we've told it a minimum a 2-dimensional minimum coordinate, and one's a 3-dimensional one. So let's just go like this. And right, we have a 3-dimensional mesh. I did mention the WebGL viewer. It's much more useful in 3D. Let's see how that goes. Right, 3D mesh. I think it's more or less what you guys should expect to be seeing.